Hi, my name is Michael. I work with David Cheriton at Stanford's Distributed Systems Group. And today I'd like to talk about a very simple kernel-level optimization for a common packet type that servers receive, which are pure TCP ACKs. And by optimizing the receive process of these packets, we show some good improvements to some server applications. So the problem we're attacking here is really the high receive overhead of pure TCP ACKs. So for instance, if you're a video server, what happens is the client sends a request to you, you pass the HTTP request, and then you send out a bunch of data on the order of a few hundred kilobytes to a few megabytes. And in return, the client simply sends back ACKs that don't contain any data because it's just a bulk data transfer. And so the server really received a lot of pure TCP ACKs. And the problem with network I/O today is that for each packet, you have to do a lot of things in order to process it. For instance, you have to perform memory allocations, you have to traverse the stack up to the right protocol layer, and so on. And so along the way, for the past 20 years, there has been quite a number of optimizations, offloading techniques that have been proposed and implemented and widely deployed to today's machines. But these optimizations are mostly for data carrying packets. For instance, there's TCP segmentation offload, generic segmentation offload in Linux, also generic receive offload on Linux for the receive side, data packets coalescing. But relatively little attention has been spent on control packets because people think, hey, these ACKs are so small, they don't take up too much bandwidth. But if you count the number of packets that these servers actually receive, a lot of them are actually pure ACKs, and it turns out that the per packet overhead is quite significant. To quantify this overhead, we did a very simple experiment. We set up two machines, one running Nginx with 4 threads, and another running curl loader, which is continuously requesting random files of a particular size. On the server host, we use OProfile to break down the overhead in different system components. So here's a sample breakdown for a 2 megabyte file. So the client requests for a 2 megabyte file, the server transmits it, gets back ACKs. As you can see in this pie chart here, the receive path actually takes 20% of all the cycles for each request. And this is comparable to the transmit path. And this is crazy because the transmit path is actually doing all the work that actually sends out useful data. The receive path is actually just receiving all these ACKs. But then the per request overhead for these two components are actually comparable. We also see a quite significant overhead in terms of memory allocations within the kernel, and is also comparable to the receive and transmit portions. And we also looked at the SNMP counters on the server, and we found that more than 99%, actually 99.95% of these received packets are actually pure TCP ACKs. And so the conclusion we have from this analysis is that pure ACK receive processing is actually quite expensive. So let's take a look at why we have these overheads. So this is a conventional Linux stack. We have the DMA ring down there that serves as an interface between the interface card, network interface card, and the driver in the software. And the driver allocates a bunch of socket buffers, which are metadata structures that serve the software interface between different layers of the network stack. So whenever an ACK is received, the drivers today do something called a copy break. So they allocate a new socket buffer and also an accompanying data buffer, copies the received ACK into this smaller buffer so that the original one, the bigger allocated one, the DMA ring can be reused for the next packet receive. And then the cloned socket buffer is passed up this network stack, up to the transport layer, and then it's deallocated once the ACK processing has been performed. So the two main overheads here are, first, we have to allocate a new socket buffer and the accompanying data buffer for each ACK that we have received. We traverse all these layers in the code only to reach TCP, do some little ACK processing, and then deallocate the newly allocated socket buffer. A better way to do this is what we call a network fast path. So the idea is very simple. So instead of doing all these memory allocations and path traversal, why can't we have a very lightweight parallel stack that implements a fast path for common packet types that we want to optimize? So on the left, we have the conventional path, and on the right, we have the fast path. So when an ACK is received, we pass it directly to a parser and demultiplexer module. The parser takes out the relevant header fields in the packet that we're interested in. For ACK processing, we're only interested in the TCP sequence number, the ACK number, receive window, and possibly the timestamp option values, which are the echo reply and the timestamp value. And we also do demultiplexing within this very low layer and find the socket that these values should be delivered to and directly deliver it to a lightweight ACK processing module in the TCP layer. So the benefits of this is now we no longer have any extra buffer allocations in the driver, and we have a very short stack traversal. There's no deallocation of any extra memory either. So how do we integrate this fastpath parallel stack into the Linux networking stack? So the fastpath provides a single function driver interface that is called net fastpath in. You pass in the socket buffer, which is for parsing, and then some flags that indicate whether you want to identify certain types of packets. In this case, we only have one in this implementation. So the function here returns a verdict, which is either the packet is consumed by the fastpath stack or sets fallback. Please handle this packet using the conventional receive stack. So in the bottom code piece, we show how the driver's receive routine, the NAPI receive routine, can be simply modified by just calling this interface function. And if it is consumed by the fastpath, you just go on to the next socket buffer in the receive ring. Otherwise, you fall back to the conventional stack. So as you can imagine, if you're a TCP connection, you receive a bunch of ACKs, pure ACKs. This is handled by the network fastpath. But then you receive a data packet. The fastpath will say, hey, this is not a pure ACK. Just go back to the conventional receive stack. This way, we can seamlessly integrate the network fastpath into the conventional stack as well. So TCP Power, which stands for Pure ACK Receive Optimization, is just an instantiation of this network fastpath for pure TCP ACKs. And the implementation consists of a few parts. So we have the parser and demultiplexer that identifies pure TCP ACKs. There is the ACK processing module that lives in the TCP layer. There's some synchronization with other threads, like process threads accessing the sockets and so on. And there's basically a 10-line driver change in the kernel as well. So in total, the entire kernel patch for this change is around 500 lines of code. And here we show, if we turn on TCP Power for the workload we were studying before, we show that for various file sizes that we're requesting, we save around 14 to 17% of the cycles per request, which is quite a lot for 500 lines of code, and such a simple change. And let's take the 2 megabyte file size and try to break down where the savings actually come from. So this figure shows the CPU cycles breakdown for 2 megabyte files per request, and this breaks down the overheads in terms of different system components. And we see that the main savings really come from the receive path as well as the memory allocation subsystem. So we see a quarter savings in cycles in the driver receive routine, which is basically the NAPI receive routine. We execute nearly half as few as half the cycles in the receive stack. And because we're doing less memory allocations, we save like a fifth of the cycles in the memory subsystem. If we look at instruction count, we see a similar pattern because we have a short stack traversal, so we have much fewer instructions executed, as well as in the memory system. So you may be wondering, hey, we have a bump in the wire now for other types of packets. Is this going to affect workloads that have fewer ACKs per packet processed? And this figure shows you the relative savings in CPU cycles if we have smaller and smaller response sizes. So on the left, extreme left is 1 kilobyte response sizes. So this is basically one single packet being sent out, it acts back, and then the next request comes in. And even here, we see that the optimization actually saves you a little bit of cycles. But the main point here is that by introducing a parallel stack here, we're not introducing any performance regressions to the existing receive routines. And we also ran some netperf round request response tests, and we didn't see any throughput degradation at all. So next, I'd like to present like a case study which applies this power optimization to ActBased reliable multicast. So why do we want reliable multicast? Because in data centers today, you might have to do a large-scale data distributions, such as large-scale software update to tens of thousands of machines, and you need to do it reliably. So the idea of ActBased reliable multicast is to leverage TCP's congestion control and flow control mechanisms so that we can introduce IP multicast savings without adversely throttling other TCP flows. So in TCP SMO, the sender maintains a per receiver TCP control block. It multicasts data through IP multicast, and in return, it gets back a bunch of ACKs from the receivers. And using these ACKs from the receivers, it can update the congestion control state in order to maintain fair bandwidth usage. And the problem here is because the receivers all ACK the same data, we have an ACK implosion problem. We have to process all these ACKs to update the state. So the idea is to try optimizing the ACK processing overhead as a server with TCP Power. And here I show a simple test of transferring 300 megabytes on a gigabit Ethernet over a number of receivers from 88 receivers to 168 receivers. And as you can see, without TCP Power, the transfer time just goes up all the way, while with TCP Power, we can achieve a linear scaling, near linear scaling of the protocol, of the SMO protocol. And I have also noted that the optimal is down there in the dotted black line. This is the time it takes without any overhead to transfer one copy of the file to a single receiver. In terms of per ACK processing overhead in SMO, we see that Power can save up to half the cycles per processed ACK, and this is because of a 43% savings in terms of instructions executed, as well as better usage of the L2 cache, where we're having 22% less L2 cache misses per ACK. So to conclude, we have showed that the receive overhead of pure TCP ACKs is significant in some applications, and we've proposed a network fast path, parallel stack, and used it to optimize per ACK processing overhead. And this is mainly done by minimizing memory allocations and instruction count, and we have demonstrated how to use a small kernel patch without application changes to achieve this optimization. Using this optimization, we showed non-trivial improvements with a server application as well as reliable multicast. And we expect that with growing link speeds, the per packet overhead at the end host is only going to get more expensive. So we think that fastpath-like optimizations could be very useful going forward. And thank you. I'd like to take questions now.
All right, so we'll do questions now. And after this, we have Andrew coming up to do a presentation.
Christopher Stewart, Ohio State. Did you do any sensitivity analysis across different TCP configurations? In particular in your first study. So what if I change congestion windows, et cetera, et cetera?
We did not do TCP sensitivity analysis, so we just used a vanilla Linux configuration. We were running Debian 6.0 and a Linux 3.2, which means your memory sizes, your memory socket buffer sizes are like 2 megabytes and 6 megabytes maximum. And congestion control is cubic. And we have slow start after idle enabled, initial congestion window of 10. So that's the.
Do you think that that would affect the the percentage of only ACKs that you're seeing coming back? Right, that's a really high number. That.
So I think. Okay, so if you increase, so for instance, if you so first of all, if you fiddle with, say, the initial congestion window, you're going to get lower throughput depending on how you configure it. And certain other features like TSO or GRO could also affect how many socket buffers you keep in the transmit queue and how the ACKs would affect the processing of the retransmission queue. So in here, we have TSO enabled on the server. So each ACK that comes in may cause some may cause some fragmentation overhead in the retransmission queue. So if you only have scatter-gather enabled without TSO, then we expect the performance to actually get better. Because if you're talking to someone that doesn't have GRO enabled, and there's no point of batching a large packet and sending it out back to back. So yeah, thanks.
For you.
Yeah.
I liked the, you found a good opportunity for optimization, and I like the nice layered architecture you used for inserting your fix into the kernel. That was a nice generic approach. Can you anticipate any other opportunities where you can use a fast path hook like that?
Yeah, so other packet types, basically, right? So
which ones are going to have, I mean, it's not worth doing unless there's a mode where there's a lot of these packets showing up.
Yeah, actually one intriguing scenario is if you're receiving a SYN flood, then you could use it to drastically reduce the amount of time to deliver a SYN to the TCP layer. So that's...
Do we have a question? Time? Yeah, so I have actually two questions. One is, so you measured the overhead or actually savings for a very short TCP transfer. But I understand that your changing the driver intercepts all the packets, and then if the packets don't belong even to TCP, there is a little bit of bump on the wire anyway.
Mm-hmm.
So have you looked at the overhead for, say, UDP-based traffic, or for the traffic where there is a two-way communication, so there is not too many just pure acknowledgements coming in?
Yeah, so for this, like I showed the smaller response sizes, so that kind of answers the request response type of workload. So we show that even there you save like 2% of the cycles. So for UDP, so how the parser works is it gets the SK buff, it looks at the packet payload, looks at the Ethernet header, sees that, hey, this is an IP packet, looks at the IP packet, hey, this is a TCP packet. So if it's UDP, it stops there and then goes to fallback. So this might be, on the surface, it seems like, hey, you're doing extra work because you're parsing. But actually, if you do very fine-grained instrumentation within the driver, the main cycle's expenditure is actually stalling while waiting for the packet headers to be retrieved from the memory. So because there's a cache miss there. So the parser incurs this cache miss instead of, if you use the parser incurs this cache miss, but if you don't use the parser, you still have to incur that cache miss in the GRO layer in Linux when it actually looks at the Ethernet segment and then the IP packet. So you could say that, oh, I'm executing a few more instructions doing the duplicate lookup of what this IP protocol field is, but that in comparison to the cache miss that you're incurring for the packets is going to be pretty expensive. It's going to be pretty low. Yeah.
One last question at this mic, and as quickly as we can, then you grab them out after. Thanks.
Yeah.
Okay, Ericsson, thank you. This is really interesting. One question: when will I be able to download this from the official Linux kernel?
It's tricky because they have a very stringent policy about integrating stuff that kind of sits on the side. But I do maintain patches for various Linux versions, so come talk to me if you want to use it. Yeah. Thank you.
All right, thanks again.
Yeah.